So welcome to the session on Schnorr Signatures and Applications. The first talk, so we will have three presentations. The first talk is on distributed Schnorr signatures, and the speaker is Yeping Ma.
It works, right? So hi, today I'm gonna be talking about Sprint, which is a suite of protocols for batch signatures in the threshold setting. And this is a joint work with Fabrice, Shai, Hugo, and Tao. So to start, let's, so to begin, let's do a quick warm-up on signature schemes. So here we have a signer who generates a pair of secret key and public key. So SK is signing key and PK is the verification key, and the verification key is made public. Then if Alice wants to send a message, it computes the signature using the SK and attach it to the message. Whoever receives this message can use PK to check that it is indeed Alice's message. Roughly, we say a signature scheme is secure if anyone without the secret signing key of the person cannot create a signature on behalf of the person. So it means that if the attacker tries to send assign a message on behalf of Alice, then Bob can again use PK to verify that this message is not Alice's message. Okay, so as we know that the security of signature schemes are mathematically based, but from the system perspective, the security really relies on keeping the signing key secret. So in practice, the secret key is stored on a device like your laptop or some server, and this creates a single point of failure. So threshold signature is introduced with the goal of raising the bar for the attacker by splitting the secret key into pieces and storing them on different machines. But now signing with the pieces becomes challenging because we don't want to reconstruct the secret key at any point during the protocol execution, but we want to generate a signature that looks like it is signed by a single party using the false secret key. So this, in fact, requires non-trivial protocols run by the parties. And similarly, we say such a protocol is secure if the corrupted set of parties cannot forge signatures. So one compiling application of threshold signatures that many prior work has considered is crypto wallet, where the secret key is split across a few personal devices. And then when the user issues a transaction, these devices talk to each other and generate a signature. But in this work, we consider the setting of a large set of parties. So for example, implementing distributed signatures on blockchain, where the number of parties is in the hundreds. So usually the cost of the protocol scales with number of parties. So if we were to run the existing protocols on a large number of parties, then it is expensive to even sign a single message. So our first idea here in this work is to alleviate such cost by sending many messages with only one run of the protocol. So even if the cost is high, we can amortize this cost over many messages. But this is not enough. Recall that we have many parties, so it's likely that some of them act maliciously during the protocol execution and then make the signing fail. So, so this completely defeats the benefits we just got because we need to rerun the protocol, and likely this crash down will happen again. So to make the first insight useful, we want to eliminate the effects caused by the malicious parties, either by detecting them or an indirect way to remove these effects and to ensure outputs. So here comes the high-level properties of protocol. So Sprint is a secure signing protocol with guaranteed output delivery in the asynchronous setting. So we call this robustness here. At the high level, it has a two-round message-independent preprocessing phase, followed by a one-round non-interactive signing phase where it can sign many messages at once. So to specify, let's say we have n parties with 1/3 of them being corrupted, then Sprint can generate n minus 2t signatures. So note that this 3T plus 1 is already optimal resilience if we want robustness in the asynchronous setting. But if we're willing to sacrifice a little bit on resilience, we can introduce a parameter A here that indicates the trade-off between the resilience and the number of signatures that we can generate. Then with 3T plus 2A minus 1 parties, Spring can generate A times n minus 2T signatures. So this is a multiplicative factor of A from what I showed before. Concretely, let's say we have T equals n over 4, and T is the corrupted parties. Then we can generate n squared over 16 signatures. Generally speaking, if we have a constant fraction of corruption, then we can generate quadratic number of signatures in n, and that in turn gives us a constant amortized cost per signature. So here we're counting the communication cost as the number of broadcasted group elements, and we view the broadcast as a black box. And then these numbers will get better if you have less corruption. So for example, if T equals n over 5, then we'll generate more signatures with smaller amortized cost per signature. Okay, so before I present the main techniques of Spring, let's start with some basics of Schnorr signature. So in Schnorr, we have a group of order G, and the signing key S is just a random element from ZP, and the verification key will hide the secret on the exponent of the generator. So over this talk, I'll use additive notation for the groups. The signing process is very similar to a zero-knowledge proof of discrete log. So to sign a message M, the signer will first choose this random element, secret element, R from ZP, and then compute little r dot G, and we call this as pre-signature. So note that this pre-signature is message independent, and also keep in mind, we'll use the fact later that R being random is very essential for security. Next, after the signer knows the message, it can compute the hash of the message together with the pre-signature and the public key to generate the value E. And then it computes a simple relation, phi equals R plus ES. And finally, the signature consists of the tuple, the pre-signature capital R, and the value phi. So don't worry about the steps. It will appear many times in the talk. Then the verification is relatively simple. It recomputes the hash exactly as before, and then check the relation phi equals R plus ES, but on the exponent of G. Okay, so in threshold version of Schnorr, the signing key S is secret shared among multiple parties. So in this talk, we assume that S is already shared, and we focus on how to compute the signatures. So to sign a message M, now all the parties need to jointly run some protocol. The first step is to generate some sharing of the secret value R, and then compute the pre-signature. And this is what we call the so-called pre-signature generation, and it's also the pre-processing phase here. And then after all the parties know the message M, they can compute the hash exactly as before. Then each party holding a share of S and a share of R can compute a share of the signature phi locally as this. And then finally, everybody can reconstruct the signature using the shares of phi. So this is a high-level picture of how Schnorr signature works. But this strawman only signs a single message, so the M here. Also, depending on the pre-signature, it may not be secure or robust, which is not the property, which we want the properties of security and robustness. So, so in this work, we introduce a set of techniques that achieves our ultimate goal. The first technique is extreme packing, which allows us to generate sharing of many randomness and many pre-signatures. And then in the online signing phase, we have some simple a single instruction, multiple data tech trick that allows each party to locally perform a simple operation on share, but that results in signing multiple messages. So the two techniques together allows us to sign many messages at once. But recall that this is not enough. We still want our protocol to be secure and robust against malicious parties. So we introduce an agreement protocol that allows the parties agree on those randomness that are sufficiently good to give a secure and robust signing. And this agreement protocol has the early stopping feature, and it only requires 2 runs. So in this talk, I'll focus on the first technique and then briefly discuss the second one. So the packing technique is orthogonal to security or robustness. So to get the essence of the idea first, let's, for now, don't worry too much about malicious behavior. So I'll first describe a strawman that outputs a single pre-signature and then extend the strawman to output many pre-signatures. So the sketch here is just 1 round, very simple. Each party contributes a random polynomial to the randomness little r. To specify, each party acts as a secret sharing dealer, chooses a polynomial, a random polynomial of degree t, and then sends the shares to all the other parties. So every party does the same. Then each party will receive n shares. So for example, P1 will receive all the shares marked in green. And they will locally add up the shares together, which results in h of 1 up to h of n, where h is the sum of all the contributed polynomials. So now the polynomial h defines the signing randomness r that we want, and each party holds a Shamir share of the random value r. So to compute the pre-signature, we also have each party broadcast a group element. Pi will broadcast hi of 0.g, and then all the messages marked in green will be seen by all the parties. Now they will do addition in the group over these messages, and that results in h of 0.g. And note that h of 0 is the little r, which is exactly what we want. So this is the pre-signature r. OK, so now we're going to extend the previous protocol to compute many pre-signatures. And the main trick is pack secret sharing. So in standard Shamir secret sharing, we hide the secret at the point 0, and then define the shares at point 1, 2, and so on. So the red points here are secrets, and then blue points are shares. In pack secret sharing, we can hide the secrets at point 0, -1, -2, etc., and then choose a polynomial that interpolates the red points, and then define the shares at 1, 2, 3, and so on. So note that in pack secret sharing, even if we share multiple secrets, each party still holds a single share. So now with this technique, we can just do a slightly modification to the previous protocol by having each party share a polynomial of degree t plus a minus 1 that hides a secrets. So after they rerun the protocol with this change, the parties will get a sharing of a random values, R1 up to RA. And with some actual work, but not X around, they will get the pre-signatures capital R1 up to capital RA. OK, so now we have everything we need to generate signatures. We have sharing of A random values. We have the pre-signatures. And after we know the A messages, we can compute the hash. So we get A public values, E1 up to EA. But computing the signature phi is actually not trivial. So let's first take a look at a simpler example where we just want to compute Rk plus S, where k is from 1 to A. So now that we have the sharing of R1, R2, etc., but recall that we assume the signing key S is secret shared using a degree T polynomial. So now if each party holding these blue points, they add up the shares together, the resulting point is going to interpolate a polynomial. The resulting point is going to define a polynomial that interpolates the points R1 plus S, but not R2 plus S, and not R3 plus S. So basically, this means that it still works for one signature, even with pack multiple randomness here. So a simple fix is to also assume the secret signing key S is shared in a packed way, namely A multiples of S. So now if each party locally adds up the shares together, so adds up the blue points together, then the resulting points will define a polynomial that interpolate R1 plus S, R2 plus S, and so on. So this is what we want. We solve the problem. But recall that we still want to deal with the product EK here. So usually, because EK is public, so everybody can multiply this public value with the shares. But let's see what happens if we multiply with E1. So if the party multiplies E1 with the local share, then the resulting polynomial will interpolate the points of multiple E1 times S. So that means if you add up the shares of R, then those points are going to define a polynomial that interpolate R1 plus E1S, R2 plus E1S, and R3 plus E1S. And this is not what we want. So basically, we still didn't get any advantage of pack sharing. So here, unless you can, here you can, of course, multiply the local share with E1, E2, etc. But then you need to reconstruct multiple polynomials, and this is not the efficient property we want. So our trick only requires a simple change, and that results in each party doing a simple operation on the local share and be able to sign in messages at once. So the change is that we interpolate the values E1 up to EA using a polynomial E of degree A minus 1. Because these values are public, so the polynomial E is also public. Then the pack sharing of the A signatures, so different R's plus different E's times S, can be captured by polynomial H plus polynomial E times polynomial F. So what this means? It means that each party, Pj, can locally compute the multiplication of the shares of E and the shares of F, so E of j times F of j here, and then adds with the share of the R, so which is H of j here. Of course, to have this work, we need to increase the degree of H to T plus 2a minus 2. So this results in a little bit trade-off here, because before that we have n at least T plus 1, and now we need n at least T plus 2a minus 1. But recall that we have many parties, so this little loss in resilience is actually acceptable. Okay, so now we know how to sign A messages using package sequentially. We can even boost this effect by some multiplicative factor of B using a superinvertible matrix. So recall that we define the signing randomness as sum of all the polynomials, and this is actually overkill, because if each HI itself is random, then why not use it as a signing randomness? So that means if every party is honest, every polynomial is random, then we can boost by a factor of n. But looking ahead, we also want to consider the case where malicious parties do not share random polynomials. So in that case, the challenge is that we don't know which polynomial is actually random. Here we use a classical idea of superinvertible matrix. So by that, I mean, let's say we have n polynomials, h1 up to hn, where b out of them are truly random. Then the superinvertible matrix can extract those randomness and give us u1 up to ub, where each of them are, where all the polynomials used, they're independently random. So combining this trick and the previous SIMD signing together, we result in B sharing of length and randomness, and we can sign A times B messages. Okay, so now we know. Now we know how to sign many messages, and we partially deal with the malicious case. But malicious party can actually do more, and this is handled by our next trick. So the malicious behavior that can create a huge problem later is to share a polynomial such that the reconstruction completely fails. So now here, our goal is to ensure that those parties agree on the polynomials and the good polynomials that has the correct degree specified by the protocol. So our agreement protocol only adds one additional round to the previous version I mentioned. So as a result, it only requires 2 rounds, and this is our pre-signature generation. So readers can you can check more details in our paper, but the result we achieve here is that we can have the parties agree on at least n minus t good polynomials in the asynchronous setting, where good means that the polynomial has the correct degree as the protocol specifies. So combining with the previous techniques, we can get at least n minus 2t good random polynomials. And then this is the randomness for the signing we can have. And then combined with the pack secret sharing, we can get a times n minus 2t signatures. And this is the numbers that we stated in the main theorem before. Okay, so finally, I want to mention some important details in the paper that related to security and also extended features of Sprint. So first, to have this multi-message signing work, we need to use some like different hashing and re-randomized trick that are different from the standard threshold Schnorr. Also, we cut the cost by using the Feldman commitments to polynomials, and that results in a non-secure distributed key generation. But we prove that for signature purpose, it is fine. And finally, we also show in the paper that how to set up the secret key and how to transfer the secret key from one set to another. Okay, so to summarize, our protocol can generate quadratic number of signatures, assuming constant fraction of corruption. And I want to mention here that a later work by Victor Schrupp can make the Sprint protocol concurrently secure in a black box way. So that means like many copies of the online signing phase can be run concurrently as long as sufficiently many pre-signatures are available. And then finally, an interesting question is that can we achieve a better trade-off between resilience and the number of signatures we can generate? This concludes my talk, and thanks.
Thank you very much. We have time for a short question.
I had a question on the SIMD technique. It seems to be general, and why does it only apply to when n is large? Like what happens when n is?
Oh yeah, the SIMD technique has nothing to do with n is large. So like n is large is the focus setting of our protocol, and SIMD technique is just for like signing many messages at once.
Ah, okay. So
Yeah.
Does it also improve the state of the art for a small number of parties signing?
Yeah, it works for the small number of parties, but that is not the application that we're targeting on this work.
So it also improves the small.
Yeah, it works for any.
Ah, okay.
Yeah.
Well, thanks.
Okay, thank you very much, and let us thank the speaker. Okay. Yeah, so the next talk is about distributed key generation, and the speaker is Victor Schrupp.
The microphone is working? Yes? Okay, good. So this is joint work with Jens Groth, and it's kind of very nice that Yiping gave an introduction to my talk, so all of the technical details and definitions have already been set up, so I'll focus on what's different. So our motivation is threshold Schnorr signatures. And we're mainly interested in the asynchronous communication model. Why? Because even though most papers in the community are written in the synchronous communication model, I don't think the synchronous communication model is at all realistic, and I don't know what you're supposed to do with the synchronous model when the real world is not synchronous. So that's what we want to do. We want optimal resilience. So while maybe it's okay to relax the requirements on how many parties are corrupt, like the Sprint paper does, if you can achieve optimal resilience, why not? So that's what we're going to shoot for. We want robustness, so even if some number of parties are corrupt below the threshold bound on the number of corruptions allowed, we want to guarantee that signatures will be produced, that a small number of crashed parties can't bring the system down. And just like the last talk, we'll be working in the offline-online paradigm. I'll say more about this later, but basically by using the offline-online paradigm, what we're able to do is get high throughput in both the offline and online phases, and then low latency in the online phase. So we have a new protocol. We have a number of kind of low-level protocols that you can package together to get a Schnorr signing protocol. But what we get is a protocol that has linear communication complexity. So by communication complexity, I'm counting all the bits sent by all the parties in aggregate to each other. So that means that every party is just sending a constant number of, well, group elements, say. Yeah? So every party to sign one signature in both the offline and online phase, in aggregate, when we amortize over each signature, is sending like, a couple dozen group elements, and that's it. So it scales. As n gets bigger, every party is still dumping the same number of bits onto the network. This is amortized, like I said, and it's also optimistic. And it means that if all the parties are honest, yes, we'll achieve this complexity. If some parties are corrupt, the communication complexity will degrade linearly with the number of actually corrupt parties. And if any party does try to behave in an adverse way to cause this blow-up in communication complexity, they will be caught and they will be punished. Yeah? So it's actually a very kind of nice form of optimistic complexity measurement. We're also interested in, to get high throughput, we want to keep the computational complexity to a minimum. So we actually achieve a computational complexity that's, if we just count group additions, that's the main cost. It scales as n, the number of parties, plus a term that gets smaller as n increases. So lambda is the number of bits in the group order, so like lambda equals 256 typically. So as n increases from a small number up to in the hundreds, right? The computational complexity actually decreases, which is kind of interesting. I'm not really aware of any too many other protocols, if any, in the literature that have this kind of nice property. So we're actually using the fact that we're performing a distributed computation to distribute the workload of the computation, which is kind of nice. Let me give a little bit of an advertisement for how well I think our protocol will perform. This is based on micro benchmarks. I haven't implemented this. If anybody wants to go out and implement it, I'll be happy to see that. So this is based on micro benchmarks. I tried to do some pretty careful measurements of looking at how long group operations take using a good library. This is all done with SecP256K1, and I'm using a corresponding library for that. And our schemes also, to get the good communication complexity, our scheme inherently relies on erasure coding. Turns out that there's a lot of really good libraries out there these days for doing really fast erasure coding. So if you ever thought that erasure coding was some kind of science fiction that you couldn't actually use in practice, forget about it. It's going to be faster than your network speed to erasure code what you need to send. And then there's some other costs, like hashing. Actually, we have to build a lot of Merkle trees in this. And this will be running on a machine that has a built-in hardware instruction to help with the hashing. So that's also very helpful. So if you look at if we just count the number of group additions, not scalar multiplications, additions, per signature, 23. That's amortized. So that's a lot less than you would, this is the number of group additions each party has to compute per signature, including both. This is only in the offline phase, actually. There's no group additions in the online phase. So Based on my micro benchmarks, this is 5 microseconds. And then there are other overheads. Like I mentioned, there's erasure coding, there's hashing, and there's also some scalar operations. And I tried to do a fairly careful estimate of how, and conservative estimate, and this should be also about 5 microseconds. So pretty good. The communication complexity per party, so if we include both the offline and online phases, this will be 24 scalars and 9 group elements. So each party, independent of how big n is, for each signature during both the offline and online phase, amortized, will send out 24 scalars across the entire internet, not to each party, all together. And this assumes batching both in the offline phase, and it assumes some batching also in the online phase. These two, unlike in the sprint, there are batching techniques we use in the offline phase, and optionally, we don't need to, but we can use batching techniques in the online phase, because if you don't do any batching, everybody has to like broadcast a share of their signature, right, in Schnorr. That immediately leads to n-squared communication complexity in the online phase. But if there are standard techniques in the literature for getting the communication down to linear in an amortized sense, as long as you've got more than order n signatures to produce. So in periods of high demand, if you're getting many, many thousands of signatures per second that you need to generate, you can easily put them together in batches and spit them out and get high throughput. So we do get, so based on my little micro benchmarks and careful calculations, I estimate anyway that a good implementation should be able to get 100,000 signatures a second, based on the CPU bottleneck. And we can also then, to keep the CPU busy, we'll just need a network connection that runs at 1 gigabit per second. So kind of a standard vanilla, not even particularly high bandwidth requirement. So that's my advertisement. So I want to mention just some things that I kind of learned along the way here. This offline-online paradigm, it goes back a few decades. And I think when it was originally introduced, people thought of it as mainly as a way of moving expensive computations from periods of high demand to periods of low demand. Yeah, like, okay, maybe, but that doesn't help you with throughput, right? And it also helps you, like, when the demand is high, you can spit out signatures quickly. But that doesn't help you with throughput at all, right? And also, it doesn't help you in a situation where you're running, a global service that's in demand 24/7. So, but it's not really the case. But the offline-online paradigm is more powerful than that. Yes, you get lower latency in the online phase because you're computing these pre-signatures in advance. But by doing the things in the offline phase, and because these pre-signatures, as Yiping talked about, are message independent, right? You can generate these pre-signatures in large batches of thousands at a time, and that means you can use faster algorithms that would otherwise be unavailable to you to exploit the fact that you're generating pre-signatures in batches. And because you're generating all of these pre-signatures concurrently, you get better CPU utilization because you're not waiting. Even though the protocol for generating, maybe we're going to generate 10,000 pre-signatures in a batch. But we're doing them all in parallel. So even if that protocol takes, 10 rounds of communication, right? We're generating so many of these things that we can kind of balance the load between the CPU and the network so that we're not sitting around waiting all the time. So because of this batching and because of the advantages that gives us, this gives us better overall throughput, even when demand is 24/7. So forget about offline-online being a way of just shifting resources from periods of peak demand to periods of low demand. It just helps with throughput altogether. So you're really going to have like one process just generating pre-signatures and spitting them out, and then feeding them into a second process that's running concurrently with that, generating signatures on request, right? And so you just have this flood of pre-signatures coming in, keeping the signing machine filled up with pre-signatures all the time. Okay, so that's enough of the kind of examples and advertisement. So there's really two main techniques that I'm going to talk about that we did. So our main idea is, one of our two main ideas is what I'll call a better batch Go AVSS protocol. So let me just define these terms. So everybody knows more or less what AVSS is, asynchronous verifiable secret sharing. Importantly, what I really want here is so-called complete secret sharing, so that we have a dealer who is supposed to share a polynomial f, and each party is supposed to get f of I, its share, right? And eventually, no matter what, right? Or, well, you know, if the dealer is honest, all the parties will get their share, and nobody will learn anything about except what they're supposed to. Privacy requirement. If the dealer is corrupt, parties may or may not get their share, but if anybody thinks they got a share, then they're guaranteed that everybody else will eventually get their share. So that's a standard completeness property. And that helps a lot, because it means that you don't need to, especially in the signing phase, you don't need to worry about proving that you've revealed the correct share, because you can just rely on error correcting techniques. You don't need any commitments. Well, I'll get to commitments in a minute. Okay, so that's secret sharing, right? I'm not talking anything here about group elements or anything, just strictly scalar-oriented secret sharing over a field. Now, for applications like Schnorr Signatures, you're going to need some group elements somewhere, right? You want to be able to essentially publish a public key, and this will be for Schnorr, this will be an ephemeral public key, one per signature, right, that you'll need. So I want to publish a public key so that everybody is guaranteed to see the same public key, and then I want to distribute shares of the corresponding secret key. That's what we need in this, right? So we want an AVSS scheme that does exactly that, and I'll call that a group-oriented AVSS, Go AVSS. So it's kind of nice to, it's not necessary, but it's kind of nice to abstract out and state precisely what it is we need here, right? So, and this is different from what typically happens in a lot of papers is they say, well, we'll use Pedersen commitments or something like that to help us build a VSS scheme, right? Oh, and by the way, these Pedersen commitments already give us the public key, the public key part that we need as well, right? But that's not what but that's like putting implementation before specification, right? This is what you need. You don't need Pedersen commitments or any kind of commitment. So I'll get to what our result is in just a sec, but we also then, so we can have AVSS and then group-oriented AVSS, and then you can have batch versions of that, where in a batch version you just, you're going to do this 10,000 times in a batch, okay? Either for AVSS or Go AVSS. So our first main result is a new batch Go AVSS protocol, which we can use in Schnorr and other applications. So what we give basically is a simple reduction from batch Go AVSS to pick your favorite batch AVSS over the same scalar field. No polynomial commitments. We don't need Pedersen commitments, KZG commitments, nothing. So, and of course, you can think in just a second like how this would work. You run the AVSS protocol, you distribute shares of your secret key, and then you also are going to use some kind of reliable broadcast to publish your public key, but then you have to somehow prove that this public key really is the public key corresponding to the secret key for these shares. And for that, we use a simple statistical test. This statistical test is actually quite efficient, and it actually you can rig it so that it gets more efficient as n gets larger. This is what I was talking about before, about distributing the work among the parties. So it's more efficient as n gets larger up to a point. So the statistical test takes lambda over n group operations, and so that would probably be too good to be true if that were the whole complexity. Like it would just go down to zero if we as n gets large. But then there's some extra work that's linear in n, scalar operations, and then the VSS protocol itself will contribute a linear term. So for this, so after this reduction, you can plug in any VSS protocol you want, and you probably would want to plug in this one, this work I did with Nigel Smart last year, which gives us a VSS protocol that works just with scalars, and it achieves this amortized and optimistic communication complexity, and it only uses lightweight crypto. All you need is a hash function. That's it. No pairings, elliptic curves, nothing, except for authenticated and private channels. How many minutes do I have? Huh?
1 minute.
1 minute? No, but I started 5 minutes late.
Yeah.
So I have 3 minutes. Oh, but there's time for, okay. So I'll talk fast. Okay. The second result is a better batch randomness extractor, and Yiping talked about this kind of thing. So each party is going to run a Go AVS as this dealer. We're going to agree using some kind of agreement protocol on a bunch of dealings. And then we're going to extract 1/3 and random-ish dealings by linearly combining dealings using a superinvertible matrix. Brief history of superinvertible matrices. Yiping talked about them. Ancient history, coding theorists just called them generating matrices for MDS codes. Cryptographers then rechristened them in the context of multi-party computation, superinvertible matrices. And I think, maybe I'm mistaken, but Sprint is the first example that I've seen actually of using superinvertible matrices in the context of public key cryptography. So the matrix is full of scalars, and you're multiplying by a vector of group elements. And so in this setting, when we're multiplying a scalar matrix by a vector of group elements, what's interesting then is the additive complexity of these matrices. So because the group operations are expensive, right? The group additions are expensive. So we can look at the number of group operations for randomness extraction, and I'll amortize per group element output. So if you think of it as a matrix times a vector, I'm getting as output a number of group elements. So basically, how much time in an amortized sense does it cost me to produce one of these outputs? Naively, if you just use quadratic matrix vector multiplication, this is going to be lambda times n. Lambda comes from the fact that you're multiplying each operation really is you have n squared operations, but each of them is a full scalar operation, right? So there's a scalar multiplication, so it's lambda n. You can speed that up using FFT techniques. That brings it down to lambda times log n. You can use Horner's rule, especially if you have small evaluation coordinates. That brings it down to n log n. So this is going to be better than FFT when n is a bit smaller than lambda. So for n up to 100 or 200, this will actually be better. And our observation is that you can use what's called a Pascal matrix, a classical gadget that's full of, it's a box full of binomial coefficients. And even though the binomial coefficients are very large, because of the basic algebra of binomial coefficients, you can get a nice algorithm for multiplying a matrix times a vector of this form, and the additive complexity is just n over 2. No hidden constant, well, the constant is 1/2. So that's how many group operations it takes to get out one output here. And in some circumstances, and particularly the example I showed you earlier, you can actually get it down to n over 3 with some extra tricks. So for lambda equals 256, this should be much better than the FFT techniques for n up to many hundreds. I think up to 1,000 should be a safe bet from what I calculated. And that's the end of my talk.
Thank you. And do you have questions? Come to the mic, please.
Thank you very much for your great result and presentation. So your title says above the DKG, but you started with threshold signatures. Of course, sometimes we sign many messages. But what if we want to just generate one key, basically public key of Schnorr, let's say, because your protocol would allow that one? How efficient would it be? Because we will lose because you report the amortized cost?
Yeah, I think it's fair to say that these techniques are not that interesting in the case of just setting up one public key. Also, our public keys that we generate here are a little bit skewed, biased in a certain way, so you might not want to use them as public keys. My feeling was that setting up a public key is something you just do once in a while, right? But then you set up the public key and you generate lots of signatures. So it's a good question, but I think it would be nice to get faster algorithms in the non-amortized case, but we don't do that here.
Okay, do you think it's adaptable to the case that we have unbiased public key?
That it has what?
I mean, can we
unbiased?
Yeah, unbiased.
That's a really good question. I've thought about that, and it seems like, you lose. I don't know yet. I can't figure out how to do it without losing a little bit, like a linear factor.
Thank you very much.
Okay.
Thank you very much. And so the next talk is about blind Schnorr signatures, and the speaker is Georg Fuchsbauer.
Thanks, thanks, David. Can you hear me? Good, thanks. Okay, so this is joint work with Matthias Wolf, who was my student at TU Wien. So we've heard about Schnorr signatures, so let me briefly explain what blind signatures are. So meet Sai, the signer, who has a key pair, and Yuma, the user, who has a message M, and they run a protocol so that Yuma then obtains a signature on the message M that verifies under Sai's verification key. And we want two properties of this protocol. The first one being blindness, meaning that Sai should not learn the message that he was signing, and he should also not learn anything about the signature that resulted from this protocol run. On the other hand, we want one more unforgeability, which means that if Sai runs this protocol n times, then no one can derive more than n signatures from that. Okay, this concept was proposed in the 80s by David Pointcheval for eCash. It was used for e-voting, anonymous credentials, and other things. And there's been some renewed interest recently due to its application in the context of contract tracing, to advanced VPNs, private relays, private access tokens, privacy paths, Bitcoin blind coin swaps. And this last application brings me to a problem that we have with currently existing schemes, which is that these schemes define their own signatures. So they're not compatible with existing schemes. So our goal here is to define a blind signing protocol for Schnorr signatures that are already deployed. So why? Because they're used a lot, they're being standardized, they're used in applications like Bitcoin. So the current state of affairs is, unfortunately, that we don't have a concurrently secure blind signing protocol for Schnorr signatures. So these applications that were proposed, they're not actually concurrently secure. So in this work, what we do is we propose a protocol for blind Schnorr signing, and we prove it's secure. We also introduce a generalization of blind signatures. And since our protocol uses kind of heavy tools, namely non-interactive zero-knowledge proofs, we also give various implementation to assess the efficiency of the scheme and its practicality. Okay, so we've seen Schnorr signatures. We have a group, a hash function that maps into ZQ. Secret keys are from ZQ. Public keys are of the form little x times g. So I also use additive notation like everyone else in this session. And to explain signing, it's actually instructive to look at what it was derived from, which is the Schnorr identification scheme. So meet Marcel, the prover, and Jules, the verifier. And the prover wants to convince the verifier that he knows the secret key X. So the way he does is he generates this ephemeral key pair little r, capital R, sends the public key to the verifier picks a random challenge C, and the prover now has to compute this element R plus Cx mod Q. And you see that if you take this equation, multiply by the generator, then you get the Schnorr verification equation. Okay, we know that to turn this into an actual signature scheme, you use a random oracle or concretely a hash function to produce this challenge value C. So this leads us to the signing protocol. So this is known to be secure in the random oracle model if the discrete logarithm problem is hard in the underlying group. Okay, so how can we define blind signing for this protocol? So let's go back to this identification scheme and see how what we can do. And the first idea would be, well, what if the user just computes this value C, hashes the message that the signer shouldn't see, and the signer replies as before. Okay, so that while the signer doesn't see the message, still this is not a blind signature scheme because the signer knows the signature, and that should also be hidden. So what Schnorr proposed is to have the user randomize these signature element that the signer sends. So the user would pick two values, alpha and beta, get this first value r, randomize it to some r prime, then hash that element r prime, also randomize the challenge that she sends, and then the signer responds as before. So seemingly completely unrelated value s to what has happened before, but amazingly, you can actually derive from this value s the corresponding second element of a valid signature. So you can verify yourself. And what's also easy to verify is that you actually get blindness. Why? Because these values r prime and c prime that the signer sees, they're perfectly blinded. And then the third value, s prime, is just the one value that makes this a valid signature. Okay, so now the question is, while we have blindness, do we actually get unforgeability? And for this, let's first look into the notion that we actually want, which is unforgeability under concurrent attack. So here's the motivation for that. So there might not only be one user, Yuma, but there would also be Usain and Yuri that all want signatures from Sai. And so say Yuri starts a signing session and then disappears into space. Then Sai can't just wait for the next message before starting a new session with someone else, because that would make him vulnerable to denial of service attacks. So we need to have concurrent sessions. So Yuma might start the session, then later Yuri comes back, sends his challenge, and then Yuma sends her challenge. Okay, so this is the kind of the situation, the scenario that we want security for. And that was also what was originally considered by Schnorr in his security proof. So he showed that if the so-called Ross problem is hard, then his scheme is concurrently secure. He actually showed an equivalence because if Ross was easy, then there was an attack against the scheme. And then much later, unfortunately, it turns out that Ross is not that hard and the scheme is not concurrently secure. This was shown by Ben Hamouda et al., who actually give a practical attack where the signer, or the adversary, starts lambda concurrent signing sessions and then can derive lambda +1 signatures. Okay, so the open question that remains is, can we define a secure blind signing protocol for Schnorr signatures? So the starting point for our protocol is Schnorr's original scheme. And when you look at how this attack works, is that the adversary receives all these R values in parallel at the beginning, and then computes its C values in a malicious way, so that they all depend on the R values. And so you would want to force the user to compute this C correctly, but that's actually not possible because C is just a random value. So what you can do to break this link between C and R is that you have the user first commit to her secrets before by having an additional first round in the protocol. And then when she sends this challenge value C, she has to accompany it by a zero knowledge proof that C was computed correctly with respect to the values that were committed. So this makes the attack impossible because the user has to implicitly commit to what C she's going to send later. But the question is, does this give us one more unforgeability under concurrent attack? And this is our main result, where we prove that if you assume that Schnorr signatures are unforgeable and your proof system is sound, then this protocol is concurrently secure. So note that here we don't need any idealized models, we don't need any non-falsifiable assumptions like one more discrete logarithm. This is all the assumptions we need to make. Okay, so now the question is this only a theoretical construction? Because if you want to actually deploy such a scheme, then you have to implement this proof system. So that's what we did. We gave 3 implementations using different zero-knowledge SNARK systems. The first 2 are Groth16 and Plonk. So them being ZK SNARKs, they're very efficient proofs that are very fast to verify. So that was no surprise in our benchmarks. However, the complex part in these proof systems is generating the proofs. So now, this really depends on what the statement is that you're proving, and in particular, what's the representation of the statement as an arithmetic circuit, which is the language that underlies this proof system. So in particular, this is determined by what elliptic curve you use and what hash function you use. So as a first instantiation, if you use so-called SNARK-friendly primitives, like the baby chub elliptic curve and the Poseidon hash function, then you get good performance. So your CRS would be less than a megabyte, and you can generate proofs in around a second. Okay, but that's kind of cheating, right? Because we said that our goal was to have a blind signing protocol for schemes that are already deployed and they use signatures. So that's why we looked at the second scenario, the Bitcoin scenario, where the elliptic curve is SegP256K1 and the hash function is SHA-2. Now the problem here is that these primitives are not SNARK-friendly at all, and if you represent the statement as an arithmetic circuit, it gets really big, and that degrades performance, and in particular we get a CRS of size 550 megabytes, and proofs take around a minute to compute on our prototype instantiation on a standard laptop. So this can still be improved a lot. But let me just mention that's not something impractical or non-deployable, because if you compare it to the first calculation of a shielded transaction in Zcash, the numbers were actually worse, and that was a deployed scheme. Okay, so as I said, the inefficiency comes from the fact that the SNARKs are not really compatible with the elliptic curve that's being used. So we looked at the third scenario, using a system by Tehrani and Sankar, who based theirs on Spartan, which doesn't use pairing. So you can use the twin curve of SegP, and so you get natively supported elliptic curve arithmetic. So our hope was that now we get really nice numbers, but this was unfortunately not the case, but we think that that's mainly due to these instantiations still having a lot of potential for improvement. But if you look at the circuit representation of the statement, that has shrunk a lot. Okay, good. Last thing I want to mention is that when you look at how this protocol works, then you see that the user proves a statement that involves the message as a witness. So what you could actually do is have the user at the same time prove any predicate about the message. And so this actually, we realized this instantiates a more general primitive than blind signatures, if you change the statement of the proof, which, to the best of our knowledge, was not considered before, and which we called predicate blind signatures. So in a predicate blind signature scheme, the signer and the user, they agree on a predicate on messages, and when they run this protocol, the signer is guaranteed that the message that he's signing satisfies the predicate, and the user, as before, is guaranteed that the signer learns nothing else. And this is actually a nice generalization of partially blind signatures. Good, so what did we get? We get blind signing protocol for signatures that are already deployed, and we can use it in all these scenarios. And in particular, some of them, like Bitcoin blind coin swaps, it was actually necessary that you had a scheme that gives you Schnorr signatures, because that's what Bitcoin will accept. So let me conclude with a speculative different application that also uses this predicate functionality. So meet Sam, the signer, who runs a cryptocurrency exchange. And Yuma now has an account with with the exchange, but she actually doesn't own her, like hold the keys to her bitcoins, but it's all managed by Sam. So the question is, can she make an anonymous Bitcoin payment, although it's Sam that has the keys? And here's a suggestion. So what Yuma could do is generate the Bitcoin transaction from an address of the signer, and then have it blindly signed, right? So no exchange would actually do that, because otherwise they might lose all their money. But we can use the predicate functionality to guarantee to the signer that what he's signing, this transaction has an amount less than some value V, and then after the signing, the exchange can just debit the user account by V, or a lot more. So this is actually the scenario that we implemented, and that leads to the numbers that I showed. Okay, that's all, and now it's time for coffee.
Thank you for the talk. Do you have questions?
Do you feel confident making a conjecture that we need this non-black box and IZK to get Schnorr blind signing?
No.
Okay.
No. This is, it works, but I'm not claiming this is necessary.
Yeah, okay, good.
Are there more questions? I have one about the CRS and the trusted setup. You didn't say anything about it.
Yeah. Oh, that was the question? Say anything?
Yeah,
about?
so
Okay.
do you need a trusted setup or
Yes,
not?
so yeah, the paper has a lot of details, so I couldn't talk about everything. So one thing that David mentioned is that Groth 16 needs a trusted setup. So either you assume that there is a trusted setup, which in a distributed blockchainish context you'd rather not. So what we show is that you can actually use Groth 16, which in earlier work we had shown to satisfy a version called subversion zero knowledge, where the verifier is guaranteed that the proof is zero knowledge, even if it's the signer that set up the CRS. So you could use that. We also give numbers of estimates of how long this verification takes of the CRS. In Plonk, you have a trusted setup, but it's universal, so you only need to run it once, or someone has to have run it at some point, and then you can use their parameters. And then Spartan is transparent, so there's no trusted setup there. So that's also an advantage of the last scheme.
Okay.
Yeah.
Thank you. Oh, okay.
Hi. So, nice talk.
Thanks.
And do you really want that additional proof part to be non-interactive? If you allow more interaction, is it okay to use interactive one?
Yeah, so in theory, it is okay. The problem is that you need concurrently secure proofs, right?
Right.
So if you introduce interaction, you have more rounds, and since you want concurrent security, you have that.
So exactly what kind of soundness do you expect for that part? I mean, concurrently extractable witness extraction or something?
No, we don't need extraction. That's actually also...
Just
yeah.
soundness.
Yeah, actually, we don't even need snarks. We need only snargs. And the reason is that in the proof, we do the extraction, if I go back, we do the extraction from the commitment. So we don't need the proof to be extractable.
I see. Okay, thanks.
Welcome.
Okay. No more questions. So let us thank all the speakers of this session, and we have the break.